We are simplifying a cubed minus 25a over 2a cubed plus 8a squared minus 10a. I would start by pulling out common factors from the top and the bottom. I mean, I think we just overall want to factor as much as we can in the top and the bottom, and then probably there will be common factors which cancel, is my guess. In the numerator, there's a common factor of a. If I remove it, I'm left with a squared minus 25. Denominator, there's a common factor of 2a. If I remove it, I'm left with a squared plus 4a minus 5, I think. 2a cubed, 4a squared minus 10a, yep. So in the numerator, that expression in parentheses, a squared minus 25, that's a difference of two squares. So it factors as a plus 5 times a minus 5. And then here, this expression in parentheses, I need a pair of numbers that multiply to negative 5 and add up to 4. That's going to be 5 and negative 1. So it factors as a plus 5 times a minus 1. This a plus 5 and this a plus 5 cancel, which leaves us with a times a minus 5 over 2a times a minus 1. Also, I guess these a's here cancel, right? This a and this a cancel. So getting rid of those guys, we're just left with a minus 5 over 2 times quantity a minus 1. 66, we are simplifying the expression 32 to the 2/5 over 81 to the negative 1/4. Well, the first thing I would say is this 81 to the negative 1/4, it's a negative exponent, so you can bring it upstairs and make the exponent positive. There's nothing left in the denominator when you do that. I wrote a 1 just for fun. There's not really any need. Obviously, you can just write 32 to the 2/5, 81 to the 1/4. And next, you're going to need to use some fractional exponent stuff. So 32 to the 2/5, yeah, that's the 5th root of 32 squared. However, I'd prefer to apply the 5th root first and then square the result. Like, I think that's going to be a lot easier to compute without a calculator. 81 to the 1/4, that's the 4th root of 81, which is 3, I think. So 5th root of 32, I'm guessing that's 2. 2, 4, 8, 16, 32, yep. So that's 2 squared. And then, as I said, 4th root of 81, that's 3, right? Because 3, 9, 27, 81, yep. So finally, that's just 4 times 3, which is 12. You might wonder, like, how did I know that the 5th root of 32 is 2 and that the 4th root of 81 is 3? Like, are you supposed to have those memorized? No. It's really just that, like, if we ask you to find a large root of some number, it's going to be something really small. Okay? Because, like, I mean, basically, like, 4th and 5th roots, when you raise stuff to the 4th and 5th power, they get big really fast. Okay? Like, 2 to the 5th is 32. 3 to the 5th is like 243 or it's huge. Do you see what I'm saying? Like, basically what I'm saying is, if we ask you to find some large root, like 4th root of blah or 5th root of blah, it's going to be something small, like 2 or 3. You know what I mean? It's not going to be 17, okay? And so you can kind of just guess and check your way through it. 67. What's wrong with this problem? It's this. The 5 should not have moved, right? This is a classic student mistake, thinking that this exponent of negative 1 here, students always imagine that this negative 1 is applied not just to the x, but also to the 5. No, it's not. Exponents only affect the thing directly in front of them. So that's one mistake. Is that the only mistake? I think so. Yeah, so that's what's wrong with it. 68. What is x? Yeah, I mean, you know, this is sort of just asking what power of 6 would give you 1 over 36. Well, if you did 6 squared, that would give you 36. We don't want 36, we want 1 over 36. So I think it's negative 2, because then 6 to the negative 2 is 1 over 6 to the positive 2, which is 1 over 36. 69, what is x? So 36 to the what gives you 1 over 6. That's kind of interesting and pretty hard, honestly, to think about off the top of your head. One thing I would say is I know how to make 36 into 6. Like, forget about 1 over 6 for a second. What would you put here to get just 6? Well, the relationship is the square root of 36 is 6. So if I put a 1/2 here, that would give me a 6. But I don't want 6. I want 1 over 6. So I think what I want to do is just negative 1/2, because then, 36 to the negative 1/2 is 1 over 36 to the positive 1/2. That's 1 over square root of 36, which is 1 over 6. So yeah, so the answer is negative 1/2. So basically, what I'm getting at in this problem is that the algebra rules about like when you're allowed to distribute and when you're not, those algebra rules governing exponents and roots are the same. Like, this first line says that exponents distribute over multiplication, and so do roots. This second line says that exponents distribute over fractions, and so do roots. And this third line says that exponents don't distribute over addition, and neither do roots. Is that a coincidence? No, it's not a coincidence. It's because roots are exponents. Like, the square root of AB literally is AB to the power of 1/2. And then since exponents distribute, I can write, oh, that's A to the 1/2, B to the 1/2. And then I can just go back and say, oh, but A to the 1/2 is square root of A, and B to the 1/2 is square root of B. So the rules governing roots and exponents are the same, because roots are literally exponents. Okay, so that's why. Okay, so we're just simplifying now. 71. So I have 3a to the negative 2 to the third times 3a to the fifth. I would probably start by distributing this 3 here to these two guys. So they're both going to get raised to the third power. 3 to the third is 27. A to the negative 2 to the third, you'd multiply those exponents, so that's going to be a to the negative 6. Leave this guy alone. I have 2 coefficients. You can multiply them. 27 times 3 is 81, and then you have, a to the negatives. And then if you multiply these two guys, a to the negative 6 times a to the 5, you would add those exponents, so that's a to the negative 1. That's 81 over a. 72, okay, there is no 72. Sweet. 73. Negative 4 x to the third quantity squared times 3x to the negative 2. I'd start by taking care of the stuff in parentheses. You're going to square everything that's in here, including the negative 4. So it's like negative 4 squared times x cubed squared times 3x to the negative 2. Negative 4 squared is positive 16, and then x to the 6th, and then times 3x to the negative 2. And then 16 times 3 is 48. X to the 6 times x to the negative 2. You'd add those exponents, so that's x to the 4. 74, we have 3n squared to the negative 1 times 3n squared to the 7. There's a couple ways you could do this. Like, you could distribute this negative 1 to these two things here, and then distribute the 7 to these two things here. You can do that, but like what I'm noticing is that this guy, 3n squared, is exactly the same thing that appears right here. And you can kind of take advantage of that to make this problem faster, because it's basically like, it's like x to the negative 1, x to the 7, right? I have something to the negative 1, something to the 7. If you had x to the negative 1 times x to the 7, that would be x to the 6th, right? Well, I don't have x, I have 3n squared, but it doesn't matter. Like, you're just going to get 3n squared to the 6th. See what I'm saying? And then if you distribute the 6th, 3 to the 6th, and then n squared to the 6th power, you multiply, that's 12. I don't know what 3 to the 6th is. 729. Cool. So 729 and to the 12th. Great. 75. We have 2r to the negative 1 to the 4th times 4r squared to the negative 2. All right. I mean, I think I would start by distributing like the 4 and the negative 2 to the guys on the inside of the parentheses. So that's 2 to the 4, which is 2, 4, 8, 16. R to the, negative 1 times 4 is negative 4. And then here, like 4 to the negative 2. Well, actually, you know what? I think what I want to do is I'm going to view it this way. I have this object, 4r squared, all raised to the negative 2. I'm going to view this guy as one single object and just say, you know what? This whole object is being raised to the negative 2. So what that means is I put that whole object on the bottom and make this exponent here a positive 2. I think that's the cleanest way of doing this. So that's 16r to the negative 4 over, and then if you distribute like this square, 4 squared, that's 16, r squared squared, that's r to the 4th. The 16s cancel. This r to the negative 4 is going to go downstairs, right? So I actually wind up with 2r to the 4th, and I think you get whatever r to the 8th. Okay, so 76. The hint that we're giving here is kind of similar to what I said about number 74. Like you essentially have, oh, there's a negative 2 here. You essentially have like this object 2a to the negative 1 is the same as the object appearing here. So it's a little bit like you have x squared over x to the negative 2. It's not x, it's 2a to the negative 1. But nevertheless, it's like an object squared over that same object to the negative 2. If you had this expression, you'd just be like, well, that's x squared times, this x to the negative 2 goes upstairs, and that exponent becomes a positive 2, and you get x to the 4th. I mean, if you want, you can say, oh, there's like a 1 left in the denominator, but obviously that's not doing anything. So likewise, this guy here is just 2a to the negative 1 squared times, and then this whole thing like swings upstairs, and the exponent becomes a positive 2. So then what I'm left with is just like that object, 2a to the negative 1, to the power of 4, right? So just like here. I do have a bit more to do though, right? Because if I distribute that 4, I get 2 to the 4th is 2, 4, 8, 16. And then a to the negative 1 times 4 is negative 4, so 16 over a to the 4th. 77. Once again, it's kind of the same trick over and over again. Like, you can make this problem really annoying for yourself if you choose to distribute everything immediately. But if you recognize, as has been the case in several of the prior problems, you have some object raised to a power times that same object raised to a power. Like, this expression is very similar to x to the negative 2 times x to the negative 3, which of course would be x to the negative 5. You can do the same thing here. Like, that's just going to be a over b squared to the power of negative 5. Then we should sort of so there's a couple ways of doing this. You can distribute the negative 5 and then like move stuff around in the fraction. I actually think it's worth knowing that like in general, if you have a fraction, say x over y raised to a negative power, that's actually the same thing as like just flipping the fraction upside down and making the exponent positive. That's a useful trick to know. The reason for that is, if you distribute the negative a to the top and the bottom, you get this. And then because these guys have negative exponents, they move around in the fraction, you make the exponents positive, and that's the same thing as y over x to the a. So you can see that this guy here is equal to this guy here. So I actually like that trick. Whenever I have a fraction raised to a negative power like this, I just say, no, just like flip the fraction upside down and make the exponent positive. It's going to make your life a lot easier. So if you do it that way, now you just need to raise the top and the bottom to the 5th power. That's b to the 10 over a to the 5. Cool, so that's 77. Here's 78. We have square root of the x squared quantity 2xy to the, 2xy to the negative 3. X to the 5th y to the negative 2. Did I type that right? Yeah. So I would simplify everything inside the root first. I would maybe just be like, well, 2xy all raised to the negative 3. I would view the 2xy as one single object, like it's in parentheses. And, this minus 3 is going to move that whole object downstairs, and the exponent is going to become positive. So I already have an x to the 5th here, and a y to the negative 2. So this 2x to y to the negative 3, it's going to go downstairs, but that 3 is going to become positive. Likewise, this, I think I'll do this in the same line. The y to the negative 2, like that should go upstairs and become positive. Okay, so now I've dealt with all the negative exponents. I think in the next line, I'm just gonna distribute the 3 here to each of these guys. So that's 2 to the 3rd, which is 8. And then x to the 3rd, y to the 3rd. And then I would next say that this x to the 5th and that x to the 3rd can be combined. That's x to the 8th. Also, this coefficient of 8 should be written first. So 8x to the power of 8, y to the 3rd. Now I can do some cancellation. Let's see. X squared, x to the 8. After I do that cancellation, you're gonna have x to the 6th left in the bottom. Y squared, y to the 3rd. After cancellation, you're gonna be left with a single copy of y in the bottom. Everything got canceled from the numerator, so there's just a 1 there. Finally, I would deal with the root. Like, you can take the root of the top and the bottom if you want. You could also think of this root as being a power of 1/2 if you wanted. Doesn't matter. Root 1 is just 1. In the denominator, like, I don't know. I don't know how they want the answer. Like, I think that's probably fine. They might expect you to, like, simplify that radical, like, pull out perfect squares. Like, 8 can be written as 4 times 2. And, yeah. So you could say, oh, like, I'm going to pull a bunch of stuff. I'm going to pull perfect squares out of this radical. 4 is a perfect square. You pull that out. It gets square rooted and becomes a 2. X to the 6th is also a perfect square. It's the square of x cubed. So when you pull that out, you get x cubed. And what are we left with? Well, we're left with this 2 and this y. So I think it's just 2y. So they might also write the answer that way. I don't really know. 79, 3x squared times x to the 4th minus x to the 6th. I would just start by distributing the 3x squared. So that's 3x to the, it's 3x squared times x to the 4th minus 3x squared times x, and then minus x to the 6th. So 3x, that's x squared times x to the 4th, that's x to the 6th, minus 3x, x squared times x is x cubed. And then after that, you might just notice that you have some like terms. This first term and the third term, they're like terms because they have the same variable and same exponent. This is 3 copies of x to the 6th minus 1 copy of x to the 6th, which leaves you with 2 copies of x to the 6th, and then minus 3x cubed. So I think that's that guy. Okay, get the same base. Cool. Like, yeah. So what value of x do you think makes this equation true? Yeah, well, obviously 7. Okay, like if you're trying to, right, like obviously if you replace x with 7, then you get a true equation. So therefore, x equals 7 is the solution to that equation. That's 80a. 80b, maybe you have to use a little bit more brain power. You have 2 to the x is equal to 2 to the power of 2x minus 3. The idea that we're getting at here is, look, the only way that this equation can be true is if the exponents match. Okay? Like you have 2 to the power of something equals 2 to the power of something else. The only way that this equation can possibly be true is if the something and the something else are actually the same. Okay, like that's the only way that that equation is going to be balanced. So actually, x has to be equal to 3x minus 3. Like the exponents have to be the same because the bases are the same. And then that's just a linear equation. Subtract 3x on both sides. Negative 2x is equal to negative 3. Divided by negative 2, you get x is equal to 3 halves. Cool. But what we're talking about in like these examples here is basically that this idea, the big idea behind these problems, and we'll talk about this during the year as well, is if you have like a to the b equals a to the c. You have two exponential expressions where the base, the bottom number, is the same. Like this actually means that b is equal to c. Like the only way that can happen is if the exponents are the same. And you can use that idea to solve equations like this, all right? That's what we just did here. Like, hey, look at this. The base is the same. 3 to the x equals 3 to the something else, right? So these two exponents have to match. 2 to the x equals 2 to the something else. Those two exponents have to match. But I emphasize the bases must be the same for this argument to work, right? Like if you had 2 to the x equals 5 to the third, it does not follow that x is equal to 3. Do you see what I'm saying? Like the bases have to be the same for that argument to work. So in all these problems in 81, what's going on is the bases are not the same, right? So like you cannot conclude here that x is equal to 3 because the bases are not the same. But the idea is that although the bases are not the same initially, like at the beginning of the problem, they can be rewritten using exponent rules so that the bases actually are the same. All right. You might notice like 125 is related to 5. 125 is actually a power of 5. In fact, it's 5 cubed. So if I rewrite that 125 as, I could say, hey, look, yeah, I have 125 cubed, great. But what's 125? 125 is actually 5 cubed. So what I have here is 5 cubed cubed, which is the same thing as 5 to the 3 times 3 is 9. Oh, now I have an equation where the bases are the same. 5 to the x equals 5 to the 9. That means that x equals 9. So that's the name of the game. You use exponent rules to rewrite stuff so that it has the same base. In this next problem, I have 8 to the x is equal to 1/2 to the power of 6. Again, the bases are not the same, like 8 is not equal to 1/2, but you can rewrite them so that they are. The idea, in all of these problems, the bases are all powers of the same number. In this case, 8 and 1/2 are both powers of 2. They're both powers of 2, all right? So I'm gonna replace 8 with 2 cubed. And I'm gonna replace 1/2 with 2 to the power of -1, all right? Now I use exponent rules. 2 to the 3 to the x is 2 to the 3 times x. And then the right-hand side is negative, right? The exponent is -1 times 6 is -6. Oh, now I have the same base on both sides of the equation. So now the exponents have to be the same. So now I can equate the two exponents. 3x is equal to -6. X is equal to -2. 81C. I have, good God, talk about a small font. What does that say? 3 to the power of x squared over 3 to the x equals 9. First of all, a comment on this. You might look at the expression 3 to the x squared and be like, well, isn't that just 3 to the 2x? This gets back to, if you remember, there's this true-false question earlier in the worksheets. This guy right here, true or false, a to the b to the c is equal to, and I said this was false, okay? That's actually related to the reason why this guy here, the 3 to the x squared, is not 3 to the 2x. Like, it's definitely true, okay? It's definitely true that 3 to the x squared, like that is indeed equal to 3 to the 2x. That's true. But if that's true, then what about 3 to the x squared? Like, what does that mean? Well, the thing is, 3 to the x squared could theoretically be interpreted in two different ways. Okay, like this expression could mean, in principle, it could mean either this, right? In which case that expression really would be just 3 to the 2x, or it could also mean 3 to the power of x squared, like that. Okay, and in the true-false question earlier, we tried to convey that these two expressions are not the same. They are not the same, all right? So if they're not the same, then which one does this mean, right? Which one does it mean? It means this one. Okay, now why? Like, how are you supposed to know that? Well, I'm telling you now, okay? But the reason that it means this one and not this one is the following. Anytime somebody writes a repeated exponent like this without any parentheses at all, they mean this. Because if they meant this, they wouldn't write 3x squared. If somebody meant this, they wouldn't write this. They would just write 3 to the 2x. Do you see what I'm saying? Because if this expression meant 3 to the x all squared in this sense, well, that expression can be simplified to just 3 to the 2x. And if that expression can be simplified to just 3 to the 2x, why would you write 3x squared when actually you mean something much more simple? On the other hand, this expression cannot be simplified, okay? So if somebody writes this, they mean this, all right? Anyway, there's a lot going on in this problem. But anyway, so that's what that means. What you're supposed to do is you're supposed to say, look, everything here is a power of 3, okay? Including that 9. So I'm trying to rewrite both sides of the equation so it's like 3 to the 1 thing equals 3 to the something else. That's my goal. The left-hand side, look, you have 3 to the power of something divided by 3 to the power of something else. You can just subtract those exponents. That's just 3 to the power of x squared minus x. And then on the right-hand side, 9, that's 3 squared. Okay, now I have the same base, which means I'm allowed to equate the exponents. So that's x squared minus x equals 2. Yeah, okay, well that's a quadratic equation. So I can solve that. X squared minus x minus 2 equals 0. So I'm looking for a pair of numbers that multiply to -2 and add up to -1. I think that's -2 and 1. Right, so I think that's how that guy factors, which means my solutions are x equals 2 and -1. Man, there's no way that people are going to be coming to this video to understand what is going on with that problem. I don't know. People are going to need help with that problem. That's pretty hard. All right, 81D. 4 to the x minus 5 equals 8 to the x plus 2. Yeah, this is much easier. Everything's a power of 2. So that's like 2 squared to the x minus 5 equals 2 cubed to the x plus 2. So I can multiply these two exponents. Oh, you might think, by the way, like, you might be like, oh, 4, that's, you might think, look at this 8 and be like, oh, that's 2 times 4. That's true, but it doesn't matter. 8 is not a power of 4. Do you see what I'm saying? Yeah, 8 is a multiple of 4, but that's not what we're trying to do here. We're trying to rewrite all the bases as a common power, not a common multiple. Everything here is a power of 2. Anyway, you multiply these two exponents. It's sort of interesting because 2 times this exponent here, all of x minus 5 needs to get multiplied by 2. So like, it's not just 2 to the 2x minus 5, it's actually 2 to the 2x minus 10. Because you need to multiply the entire expression. Likewise, on the right-hand side, like, you multiply 3 by x plus 2, all of x plus 2 needs to get multiplied by 3. So you get 3x plus 6. Okay, now I've got the same base. I can equate the exponents. That's going to give me this guy right here. So I equate the exponents. Linear equation, I don't know, like, subtract 3x on both sides, I get -x. Add 10 to both sides, I get 16. So apparently x is 16. 81E, I have 1 over 27 is equal to 3 to the 2x plus 1 over 3 to the 4x. So everything here is a power of 3, so I'm going to try to utilize that fact. 1 over 27, well, 27 is definitely 3 cubed. Let's just start there. And then on the right-hand side, I have 3 to the power of something divided by 3 to the power of something else. Well, that's just 3 to the power of the first thing minus the second thing, right? And then I can say, well, look, like 1 over 3 cubed, isn't that the same thing as just 3 to the power of -3? So that's the left-hand side. The right-hand side, 2x plus 1 minus 4x, that's -2x plus 1. Okay, now I've got the same base. I can equate the exponents. So negative 3 is equal to negative 2x plus 1. Subtract 1, I get negative 4 is equal to negative 2x. Divide by negative 2, I get x is equal to 2. 81f. Square root of 2 to the 2x over 2 to the power of 4x minus 2 equals 32. Okay. So, yeah, so I would say that everything here is a power of 2, so we're going to try and utilize that. First of all, so I can tell you right away, people are going to make a certain mistake. Here, you have 2 to the power of one thing divided by 2 to the power of something else. So that means you can write that's 2 to the power of the first thing, 2x, minus the second thing, 4x minus 2. Like I'm just going to subtract the exponents. The problem here is I should be subtracting all of 4x minus 2. I'm supposed to write down 2 to the power of this exponent minus that exponent. But what I have here isn't really this exponent minus that exponent, because this minus sign right here isn't being applied to the entire second exponent. It's only being applied to the first term of that exponent, the 4x. I need to make that minus sign apply to both of those terms. Now I actually have 2 to the power of this exponent minus that entire exponent, right? Without the parentheses, you're not really subtracting that second exponent. You're just subtracting the first term of that second exponent. So that's the mistake people are going to make in this problem. 32 is some power of 2. Was it 2 to the 4th, I think? 2, 4, 8, 16. No, it's 5. 2, 4, 8, 16, 30. Yeah. Okay, so that's... So you distribute that minus sign. It's 2x minus 4x plus 2 equals 2 to the 5th. Okay, and then, so 2x minus 4x, that's negative 2x plus 2 equals 2 to the 5th. Okay, after this, you might be inclined to say I should square both sides. You can square both sides, like to get rid of the root, that's fine. But you could also, on the other hand, just be like, well, taking the square root of that expression is the same thing as raising it to the 1/2. And then you have a power of a power, so if you distribute the 1/2, then you get negative 2x plus 2 times 1/2 equals 2 to the 5th. So that's 2 to the power of negative x plus 1 equals 2 to the 5th. So therefore, negative x plus 1 equals 5. So negative x is equal to 4. So x is equal to negative 4. Cool. 82. Exponent rules allow us to rewrite an expression in many different ways. Circle all the expressions that are equivalent to 2 to the power of 3x squared. I would start by simplifying that original expression as like a baseline. That's a power of a power, so you multiply these two guys. So that'd be 2 to the power of 6x. So I'm just going to figure out like what's equivalent to that. This guy, no. That guy cannot be simplified. For an explanation why, you should listen to my explanation of problem 81C. So yeah, that's essentially why. This guy here, oh, what? Yeah, no, that's definitely not equivalent. Like, there's no way to get rid of that x squared. Like, that x squared, like, it's, that x squared is not, like, it does not mean, that expression there does not mean this. That's not what this means, okay? If it meant this, then you could multiply the 2 and the 9x and get like an 18x and stuff, but that's not what it means, okay? So that's just not equivalent. 8 to the 2x. Maybe that's equivalent. Let me look at this. What is this? 2 to the 6x. You know what that is? Another way of thinking about that is 2 to the 6th to the power of x. So that's, what is 2 to the 6th? 2, 4, 8, 16, 32, 64. So that's 64 to the x. Maybe that's the best way of writing this original expression. I think this guy is equivalent. because 8 to the 2x could be rewritten as 8 squared to the x, which is 64 to the x. So it definitely looks like C is equivalent. Oh, and D is obviously equivalent, like we just did that, right? So C and D, E is not equivalent. Again, like that quantity there, 8 to the x squared, it means like this. Sorry, hold on. It means this, not this. Right? If it meant this, you could simplify that, and it would be equivalent. But it doesn't. Okay, that guy can't be simplified. 4 to the 3x. Yeah, I think that's equivalent because you could think of that as 4 cubed to the x. So that's 64 to the x. So yep. So E. Or sorry, that's not E. That's F. So F is equivalent. What? G 4 to the 6x? I don't think. No, because like that you could rewrite that as 4 to the 6 to the x. I don't know what 4 to the 6 is, but it's not 64. It's some kind of giant number, right? 4096, so that's it. So C, D, and F. 83, circle all the expressions that are equivalent to 1. These two guys, you would add the exponents, y to the 1/2. So it'd be y to the 1/2 plus 1/2, which is y to the power of 1, which is y. It's not 1. So not that guy. This guy here, you'd add the exponents, you'd get y to the 0. That is equivalent to 1. So B, yes. These guys here, no. Like you would add those exponents. I think they're, yeah, I don't know. No, you would add those exponents and you'd get like y to the like 17 over 4 or something, which is definitely not 1. This guy here, no. Like 4 to the, they're kind of baiting you here into thinking, oh, maybe like 4 to the 1/4, maybe that means 4 times 1/4. Well, it doesn't. Like that means the 4th root of 4. It doesn't mean 4 times 1/4. You know what I mean? I don't know what the 4th root of 4 is, but it's not 1. This thing here, that is 1. That is actually 1 because 3 to the 2x over 3x squared, you know, you can use that exponent rule on the bottom. That's 3 to the 2x over itself, which is, yeah, which is indeed 1. So B and E. Yeah. Oh my God. Okay. So it's just like 16 more of these, evidently. Okay. So 84A. Okay, well, I'm going to go through these quickly because there's just so many of them. So I'm going to rewrite the left-hand side in this way. That's 2 cubed to the x, so that's 2 to the 3x equals 2 to the 6th. I've got the same base, so therefore 3x is equal to 6 and x is equal to 2. 84b, I've got 9 to the 4x equals 81. Everything here is a power of 9, so I'm going to rewrite that this way. So I've got the same base. Now I can equate the exponents. I got x is equal to 1/2. 84c, I've got 8 to the x minus 1 equals 2 to the x plus 1. Everything here is a power of 2. That's 2 to the 3rd to the power of x minus 1 equals 2 to the x plus 1. So if you multiply those two exponents, you get 3x minus 3 equals 2 to the x plus 1. I've got the same exponents, so now I can equate, I've got the same bases, so now I can equate the exponents. If I subtract, so 2x is equal to 4, so x is equal to 2. 84d is 9 to the x equals equal to 3 to the 10th. Everything here is a power of 3, so that's 3 squared to the x is equal to 3 to the 10th, so that's 3 to the 2x is equal to 3 to the 10, so therefore 2x is equal to 10, so therefore x is equal to 5. 84e, I've got 8 to the x is equal to 2 to the x times 4 to the 9th. Everything here is a power of 2, so that's 2 to the 3rd to the x is equal to 2 to the x times 2 squared to the 9th. So that's 2 to the power of 3x is equal to 2 to the x times 2 to the power of 2 times 9 is 18. And then 2 to the 3x is equal to 2 to the power of 18x. Okay, so it's, oh, that's kind of, or sorry, not 18x, 18 plus x, right? So therefore 3 to the x, or 3x is equal to 18 plus x, and 2x is equal to 18, so x is equal to 9. Number 84f, 27 to the 1 minus x is equal to 1 over 9 to the 2 minus x. Everything here is a power of 3, so that's 3 cubed to the power of 1 minus x is equal to 3 to the negative 2 to the power of 2 minus x. So that's 3 to the power of 3 minus 3x is equal to 3 to the power of negative 4 plus 2x. Okay, so therefore 3 minus 3x is equal to negative 4 plus 2x. So, yeah, so 7 is equal to 5x, I think. Yep. So 7 over 5 is equal to x. 84g, 4 minus x to the 1/2 is equal to 8. This is like not an exponential equation at all. Like this is essentially just 4 minus x square root equals 8. You should square both sides to get 4 minus x is equal to 8 squared, like in other words 64. So so negative 60 is equal to x. 84h 1/2 to the 4 minus x is equal to 8. So that's 2 to the negative 1 to the 4. I mean, everything here is a power of 2. So that's 2 to the power of negative 4 plus x is equal to 2 to the third. So negative 4 plus x is equal, negative 4 plus x is equal to 3. So x is equal to 7. 84i 2 to the x squared over 2 to the x is equal to 64. Everything here is a power of 2. So that's 2 to the power of x squared minus x is equal to 2 to the, is that 5? 2, 4, 8, 16, 32, 6, no, it's 6. So therefore x squared minus x is equal to 6. That's a quadratic, so you should put everything on one side. That factors as x minus 3 times x plus 2, right? Multiplies to negative 6 and adds up to negative 1, so you get x equals 3 or negative 2. 84j 5 to the x squared over 5 to the x squared, which is not the same thing, equals 125. Everything here, so like that, that denominator can be simplified to 5 to the 2x, and then the right-hand side, that's 5 cubed. That's 5 to the power of x squared minus 2x is equal to 5 to the third. So that's x squared minus 2x is equal to 3. It's a quadratic. Put everything on one side. X squared minus 2x minus 3 is equal to 0. Factors as x minus 3 times x plus 1 is equal to 0. So x is equal to 3 and negative 1. 84k 1 over 9 is equal to 3 to the 2x plus 1 over 3 to the 4x. Everything here is a power of 3. The left-hand side is 3 to the negative 2. The right-hand side is 3 to the power of 2x plus 1 minus 4x. That's 3 to the negative 2 is equal to 3 to the power of negative 2x plus 1. The bases are the same, so I can equate the exponents. Negative 2 is equal to negative 2x plus 1. So negative 3 is equal to negative 2x, and 3/2 is equal to x. I'm doing these so fast. There's no way that I'm not messing up, but whatever. Okay, square root of blah, 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 blah. Everything here is a power of 2. So I'm going to utilize that. First of all, it's 2x minus quantity 4x minus 2. This problem feels familiar. Is this not like exactly the same problem that we did before? It's exactly the same as f from like way back when, except it's a 16 instead of 32. Okay, whatever. 16 is 2 to the 4th, 2, 4, 8, 16, yep. Cool. So that's square root of 2 to the power of 2x minus 4x, that's minus 2x, and then minus 2 is plus 2. Yeah, and then, you know, you could square both sides if you wanted. I'll just view the square root as like a power of 1/2 though. So multiplying the exponents, I get negative x plus 1 equals 2 to the 4th. So negative x plus 1 is equal to 4, so negative x is equal to 3, so x is equal to negative 3. All right, what's up with Bella and Nitya? Bella was studying with Nitya, and both had different ideas on how to start the following problem. Let me guess, someone's right and someone's wrong. Bella thought it'd be easier to get rid of the root first by squaring both sides, while Nitya thought it'd be easier to first simplify what was under the radical. Another student chimed in, you can start it in either way. Oh, okay, I guess they're both right. Yeah, I mean, I don't know. Like, yeah, you can square both sides. It doesn't matter. I'm just going to do the problem. Like, I think it's like, do the problem in 2 different ways. I think one way is enough. All right, let's just do... This is an awful lot. All right. So that's the original problem. Everything's a power of 3. So I'm going to rewrite everything as a power of 3. That 9 is like 3 squared. So it's 3 squared to the x times 3. You can think of that 3 as like 3 to the 1 if you want. Over 3 to the 4x equals 9 is 3 squared. And then I have 3 to the 2 to the x is like 3 to the 2x. And then times 3 to the 1 over 3 to the 4x is equal to 3 squared. And then that's 3 to the power of 2x plus 1 over 3 to the 3 to the 4x equals 3 squared. And then that's 3 to the power of 2x plus 1 minus 4x equals 3 squared. And then that's 3 to the power of negative 2x plus 1 equals 3 squared. And then that root is like the same thing as raising to the power of 1/2. So that's, you know, you multiply those exponents. So I multiply this whole guy here by 1/2. I get negative x plus 1/2 is equal to 3 squared. So evidently negative x plus 1/2 is equal to 2. So negative x is equal to 3/2. So x is equal to negative 3/2. Okay, there it is. Congratulations, guys. This was an awful lot. Okay. Thanks for watching.